Hi everyone, thank you for joining us today. I'm going to present our research paper titled RT Blockchain Achieving Time Predictable Transactions. I'm Seung Lee, presenting on behalf of our team from SKKU's Real-Time Computing Lab. So let me first start off by talking about our lab for a bit. So our lab is led by Professor Jinkyu Lee and is located in room 26314A of the second engineering building. So we focus on a range of topics, including real-time scheduling and systems, machine learning for RT, well, RT for machine learning, so vice versa, and software-defined batteries. We sometimes actually do some mobile computing and systems, so feel free to reach out to us at jinq.lee@skq.edu for any other collaborations or questions or stuff like that. So let me first begin with an overview of real-time systems. So real-time systems are systems that operate with strict time constraints. So we need to deriving accurate results before deadline is really essential for functional correctness. For example, like we have some examples of object detection for autonomous vehicles, well, flight control for drones, VR, AR for mobile devices. So if we go a little bit deeper for an example, here is an example of autonomous driving where decisions must be made within strict deadlines. So images are processed imagine like processing input from multiple sensors like cameras and lidars in real time to make safe driving decisions. So it's like this, right? So we have a bunch of machine learning that goes on within this single vehicle, and we have to know that all of these processes are strictly done within each time constraint, right? So for such applications, timely computation is really crucial, and this is the real heart of our research. So the thing is that in real-time systems, we need the real-time scheduling. All right, so that's how the real-time systems go. Okay, now let's kind of transition to the whole blockchain systems. So, as defined by the Merriam-Webster, it's a decentralized digital database used for securely recording transactions, right? In typical blockchain systems, the whole process goes on like this. Various nodes raise transaction requests, transactions are collected and made as a block. Then the block is broadcasted and validated by other nodes. A new block is added to the chain, and the transactions are completed, right? So within this process here, where various nodes raise transaction requests and it's collected by someone or and made as a block, um, the whole problem is that we need to know which transactions should be stored within a block, right? Uh, however, current systems like Ethereum prioritized transactions by tipping fees, right? So this actually can lead to starvations of low fee transactions, and this is very problematic for real-time applications for blockchain systems. So now let's take a closer look at how the block itself is made. After like transactions are collected, a block generator is selected, and the transactions are fetched from the block generator's transaction pool, just like this. And then the transactions are stored within the block to be made as a block, right? And then the hash of the block is calculated, and then the block is finalized. So be careful to know that this process from 1 to 4 is processed within a single block time, as we're going to notate it as BT from now on, right? And the hash calculation is something that moves on like this. Let's say like block B holds information of block A's hash, and then it runs the hash function, and then block B's hash is made. So it goes on like that. So forwarded to the next block that is going to be made, right? And these hash is actually used for validations later on. So hashing, right? The hashing calculation, we just really need to know the surface of this. We're not gonna go really deep into this, but it's something like this. So block B makes like this single block generator makes block B, right? And then the block that's made is then sent to all the other people within this group, right? So, and then they're gonna calculate the hash to see if there's any problem with the block that's generated, and if they say that block B is a correct block, then they like resend the validated data, and then we can know that this block generator is an okay block generator and did not cause any problems to the blockchain system. And that's how block B is then submitted and is then put on to the blockchain system. So where are blockchain systems really used? Right now, they're only used for monetary transactions such as Bitcoin, NFTs, right? And some are used for smart contracts. But there are actually way more possibilities and way more opportunities for these blockchain systems, such as time-sensitive economic transactions, periodic status report and transactions, such as mobility as a service. And we call that MAAS. Maybe many of you kind of have heard of that MAAS, but it's a thing now these days, right? So, what we must do to make use of blockchain systems to fulfill these opportunities is that we must implement timing guarantee on the blockchain. But there are two challenges here. The first one is that the structure of blockchain does not offer a timing guarantee. To solve this, we're going to create a blockchain network with an interface supporting transaction timing constraints. And we're going to do flexible block generation for accommodating more transactions within a single block time. And the second challenge is that scheduling methodology specialized for the blockchain architecture has never been proposed until now, right? So we're going to develop a novel scheduling principles specialized for the blockchain network to guarantee the timely execution of periodic sporadic transactions without wasting the blockchain network resources. So that's what we call RT blockchain. So the name of this paper, right? So we're gonna look at this simple example of MAAS. It's a level 4 MAAS. If you don't know about this, kind of try to Google it a bit. We don't really have much time to explain this, but let's think about this. Like there's information of a subway, a bus, and a car. That's just gonna come in for every period. So a subway train, let's say line 2, that comes in every, well, 10 minutes, right? And this bus is gonna send information of the bus, like how it's doing and stuff like that, for every 5 minutes. And this car, maybe a cab, anything like that, is gonna send its information in every minute, right? It's something like that, okay? So the information of the vehicle is stored within these small squares, which are transactions. The hash transactions are candidates to be scheduled in block 1. That's going to come up right here, right? It's going to be released here. And the hash transactions will be wanting to be stored within this block and to be sent throughout the network. So we need to send this information throughout the network so that everybody knows the information of the vehicle, like how it is, how the state is, or if there's any like problems with the vehicle, or if like how many people's riding it, stuff like that, right? But if we kind of see this and like the transactions are scheduled to fit the block while not missing their deadlines. The thing is that there are transactions that could not be stored within this block, right? If you can just like briefly see this, that we only have like one blue transactions that just fits here. We have one left over right there, right? The transactions that were not scheduled are gonna be scheduled on the next block time. So it goes on like that, right? So we need to store all these transactions to each block while not missing their deadline. So that's how MAAS works, or at least that's how people want it to work right now. But the thing is that, so the problem is that since the real-time scheduling has never been met with the blockchain systems, these kind of problems has never been solved, right? So now we're going to see how periodic transaction requests work. So here's a transaction requesting node which has period T, deadline D, and transaction size of S. So it's going to release the transactions and yeta I for every period T, and the deadline is going to be right there. So what we want to do here is we want to translate this to user level, which is transaction requesting nodes level, to the slot level, which is the level of block time, right? So if we translate all of the transactions to block time, then all of the transactions just fits right into this block time range, and we can kind of easily pursue on scheduling, right? So this whole translation makes ease to the scheduling itself. So before we go on, let me just briefly kind of read the notations here. So this is real-time transactions, yeta I. So that's kind of the original transactions itself. So T is a period, D is a deadline, S is transaction size. So if we kind of translate it to slot level real-time transactions, which is going to be yeta SI, the TSI is going to be inter-arrival slots. The DSI is going to be slot unit relative deadline. SSI is going to be maximum transaction size, and then NSI is going to be number of transactions of each job within this slot level real-time transactions. So let's then look at how time is going to be put in within this whole transactions, or in how when the block is generated and validated and stuff like that. So within the transaction pool, all of this transaction is going to be just put in the transaction pool, right? We kind of need to first translate it to slot level. So as you can see here, the yeta SI to yeta SN, is all of these transactions are going to be put in within a block to the earliest deadline first order, something like that. And then the block generating node is going to be generating the block for TSD, which is transaction schedule time. So that means the time it takes to put these transactions to a block, and then ACT, which is the time it takes to schedule the hash, right? So those two are combined, it's going to be block generation time, which is going to be notated as cgen, right? And then the block file validating node is going to be receive the information of this block, and then it's going to take TFT and HCT, which is the transaction schedule, which is the traffic time, and then the hash calculation time, right? So traffic time means the time it takes for this block, the information of this block to be arrived to this block validating nodes. So this TFT plus ACT is going to be called block validation time, which is equal to CVAL, so CVAL. So when we convert all of these informations, so something like CVAL, CGen, transactions, and so on, to user level to slot level, it's gonna look something like this. So this whole translating is one of the most essential things that we did for this paper. So let's see here. For instance, there's a transaction with a period of 4 and a deadline of 25. And the SI is obviously the size of the transactions. And the block time here is 10, CGen is 2, CVAL is 1, and TFT, the traffic time, is 1 also. So with these information and theorem 1, we can just calculate stuff like this, right? So these are all just calculations for the whole translation of this user level to slot level. So with all of this, we can just now simply translate yeta I to yeta SI. So according to theorem 1, it's going to be looking like something like this. So TSI is 1, DSI is 2, SSI is just SI, and SI is 3. So all this transaction with like a period of 4 is now going to be looking something like yeta SI1. So yeta SI1 is going to have the information of yeta I1 to yeta I3 all combined within this. And then the deadline will be obviously smaller than the deadline of the yeta I1, right? Since if it goes over this line, then deadline of yeta I1 is not met. So yeta SI1 is obviously at least the same or smaller than this deadline of yeta I1, right? So it's gonna be looking like this. So that's how we convert the user level to slot level for the ease of calculation and translation and so on. So how we did this is we were actually inspired by the traditional real-time periodic sporadic task. There's something called the demand bounds function, which is actually something that's really used a lot in real-time scheduling areas. The equation looks something like this. We just put in instead of CI, we just put in SSI times NSI over BS, just that. So and made an equation of our own. So dBF of eta SI and Q. So that's how we made the timing guarantee for RT blockchain and EDFWC for conserving. And also, we kind of made something of load, which is the maximum of the total size of transaction jobs of every eta Si within eta S, normalized by the number of consecutive slots of Q. Let's just think about it as how much transaction can be put in within a single slot level transaction eta Si, right? So since transactions cannot be split and included in separate blocks, right? Obviously, a single transaction cannot be just like split in half and put in like each other blocks. The only thing that we needed to do was put load eta s to be smaller than or equal to 1.0 minus max si over bs. So there were so many equations actually up to this, but so since this presentation is not really something that goes in that deep, I just have briefly showed you how the whole real-time scheduling and the equations of doing this translation works. So just you don't really need to think deep about this, all right? So now the next part is multi-block RT blockchain. So there are scalability issues for blockchain, and it's something that has been thought a lot of within this blockchain community. So when scaling with block time, we usually do some fixed size block generation at regular intervals. If we kind of like make the block time really long, it delays the transaction process. If we make it really short, it actually create a lot of empty blocks, right? So the SOTA scaling approaches of blockchain is like something like sharding, which is splitting the blockchain network into smaller networks and layer 2 protocols such as sidechains, plasma, rollups, and etc. What we want to do here is we want to make multiple blocks within a single block time. So since we already scheduled the transactions, our RT blockchain can do this without any errors within the system itself. So here's a transaction eta n with a period of tn, dn, and sn. Again, within the transaction pool, all these yetas are just going to come in. We are going to calculate the number of blocks to be generated and schedule the tasks into the blocks. So here, all the blocks, no, sorry, all the transactions can just be inserted to the blocks like that, right? In the EDF format. And then if we kind of we can make as many blocks as possible here by the block generating node, and then the only time that's gonna take here, extra time that's gonna take here is the hash calculation time, since hash calculation time is needed as many blocks as it has made, right? Since if we make like 3 blocks here, for each block, like block 1 is going to be the hash of block 1 is going to be have to be calculated, and then the hash of block 1 is needed for block 2, the hash of block 2 has to be calculated, and then so on, right? So the only thing that is going to be lengthened here is HCT. TST is just the schedule time. So schedule time itself does not really get affected much. Only the hash calculation time is tripled, right? So the block generation time here is cgen times m, which m is obviously the number of blocks that's made. And then the cval is just cval, but cval times m. So actually, if we think about it, it's not really cgen times m, but we need to be pessimistic in the real-time system, so that's why we just said cgen times m, since we don't really Since even though the TST does not really scale up exactly as much as a block is going to be made, that's the for the pessimism we kind of use cgen times m. Well, while cval is needed for every block, right? So if we make 3 blocks, all the validating node has to validate each blocks, right? And the information of each block has to be sent to all the validating nodes one by one. The cval TFT plus HCT is scaled up as according to the number of blocks that is being made, right? So that's why cval is times m. So it goes on like that. So not really much changed. That's thanks to the whole calculation of translating the transactions to user level to slot level, and then the whole scheduling that we have done for the single block RT blockchain, right? So the thing here is the timing guarantees for multi-blockchain EDFWC. The only thing that's going to be changing is the load. Recall the load calculation equation that we have just seen before. To reduce pessimism, we just use the load star star yeta s. So let me just take you a little bit deeper into this equation. The max 1 over 2 comma 1.0 minus max SSI over BS. So what this means here is according to the first fit policy, there is always one or less blocks with less than 50% occupation. If you think about this, it's something that's very like it just comes in straight to common sense, right? If there's like no block that is occupied more than 50%, the sum of the size of transaction is no smaller than BS times M over 2, right? So the transactions, if it's fit into all the blocks one by one in the earliest deadline format, the transactions cannot be placed like this, right? Yeta 4 needs to be on the first block, and Yeta 5 obviously would be on the second block, right? This method of storing transactions to blocks obviously contradicts the first fit policy. Thus, at most, a block is occupied less than 50%, right? So at most a block, right? So in this example, at most the second block is occupied less than 50%. There cannot be a case where 2 or more blocks are occupied less than 50%. So that's how we kind of made EDFWC, but to improve our scheduling purpose and to improve scalability of the RT blockchain, we also made something called EDF lazy here, where we store blocks a little bit later on if we have much space. So let's see that within a transaction pool, there's like 6 A's, which are transaction A's. So A type is like T is 3, D is 3, and S is 0.3 block size, BS. And there's a single transaction type that comes in every period. So that's 1, 1, and 0.3 block size, right? So if we have these two types, it's within a transaction pool, it's gonna be looking like this, right? All crowded here, but B is gonna be just put in every period, while 6A's is gonna be coming in every 3 periods, right? Every 3 slots. So if we use EDFWC, that's what we have been using till now on. It's gonna be scheduled like this. The like in the first slot is this all crowded up and we make 3 blocks, but there's this for the second slot and third slot, since there's no more A's, only B is going to be stationed in each block, right? And then there's going to be this much leftover space, so that's 5 blocks made every 3 slots, right? But what's better here is to reduce the block that's being made, since the whole blocks being empty is actually a waste of space itself, right? So what we can do is we can just schedule these 8 types since the deadline is 3, right? The 8 type blocks can be stored up till third slot, right? So since we know that these transactions are going to come in periodically, what we can do is that we can make only a single block by pushing these like A's away to the second and third slots. So if we do that, only 3 blocks are made every 3 slots, so that's two less blocks being made per every 3 slots, right? So that's not wasting space and making the blockchain system more efficient, making the resource constraint more spacious, right? So for evaluation, for our implementation settings, we did a consensus algorithm of proof of stake. The block time was 12 seconds, block size was 100 kilobytes, maximum number of blocks per time was 8. Hash algorithm, we used SHA-256, experiment time was 100 slot units. So this is not really realistic, but why we have put in this implementation setting is since we need to see how our RT blockchain was run, right? So for evaluation, we first did a type A evaluation where load for yeta S for each yeta S altered by the transaction size. So the size of transaction for each load was 1.125, which is 0.1 BS, 2.25, 3.375, and 4.5, right? First of all, there were obviously no deadline misses in every scheduled transactions in EDFWC and EDF Lazy. So that's obvious since that was our primary goal. That's the whole reason we developed the RT blockchain itself, right? And this what we could also see is that EDF Lazy on average stores transactions using less blocks compared to FIFO and EDFWC. So FIFO here, it means the original like proof of stake algorithms such as Ethereum or stuff like that. So we can see that our EDF Lazy is really efficient in many ways since it stores transactions using less blocks. So which means that the EDF Lazy was efficient in storing the blocks itself, right? Storing transactions, right? So the second is that neither the size or the number of transactions are directly related to the performance of EDFWC and EDF Lazy. So as you can see here in this graph, the graph does not really show any behavioral things, right? So that's why the neither the size nor the number of transactions are directly related to performance, right? Also, we put on an efficiency test for EDF Lazy. Here is type H harmonic, where cases where the period of transactions are harmonic according to bottleneck in the system. So the period of each transaction starts at 2, 1, 3, and 9, which are common division of 9. That means that for every 9 time slots, all of the transactions are just gonna come in jamming the whole system. We purposely did this to see how the RT blockchain behaves when a bottleneck occurs, right? So for type A and type H, it comes out like that. For type B and BH, it comes out like that. So you can see that when a bottleneck occur, EDF Lazy mostly shows a really high performance, right? We also put on a performance test of low star star. So recall low star star, which was made to reduce pessimism of low star, right? Uh, for the simulation, it guarantees 17.8 to 25.1% more schedulability of transactions. So low star star does way better than low star for all types of simulation performance tests. And the relatively schedulability performance increases up to 225.8%. So two and more times of the schedulability performance. And it also shows performance increase when 0.m to 0.4m and 0.4m to 0.6m, which is 138.2% and 141.3% each. So for the conclusion and discussion, we developed an RT blockchain which does timely transactions for the blockchain systems, and we did this by doing slot level translations. So from user level to slot level, we translated with a bunch of theorems, and we also used some timing guarantees such as DBF, load, and low star star to make it possible. But for discussion, there are some discussions for network issues, security issues, and scaling issues. That is actually some of the issues that all blockchain systems kind of have. So other than that, RT blockchain is a blockchain system that first pursues the whole real-timeness within the blockchain system, making it a novel thing for the blockchain and the real-time community. So thank you for listening up to here. If you have any questions, again, just contact us through our lab or through my personal email. I'd be happy to take questions. Thank you.